All right, Eric, what did your graphs look like for your positive even integer powers? Yeah, they're like our U-shaped graphs or parabolas. What happened to the U-shaped graph as you increased from like 2 to 4, 4 to 6, etc.? What? Actually, like from 2 to 4, x to the fourth is actually steeper. Okay. Or skinnier. You might also want to know, most of you know this, that these graphs are symmetric about our y-axis. All right, let's look at now making those integer powers a negative. Jack, what did the graphs look like for your negative integer powers when they were odd? Okay, so what quadrants were they in? Yeah. Okay, so as we went from like -1 to -3, they got closer to the axes. Okay, all right. The one thing that we need to discuss for this and then the other negative integer power are asymptotes. Where do we have asymptotes for these graphs? Okay, so you're right. The y-axis and the x-axis are both asymptotes. The one thing that you are going to be asked to look at quite a bit this unit is what happens as x gets either really close to 0 or as it approaches infinity. So here's what I mean by that. So obviously this is your x-axis. As our x values approach infinity, okay, infinity is like a really big number, right? So as your x values get closer and closer to a really big number out here, what happens to the graph? So as we are approaching infinity along the x-axis, what happens to this graph? What is it doing? It keeps getting closer to the x-axis, okay? What happens, I guess I should phrase it this way, what happens to the y values basically is what we have here. What happens to the y values as we approach infinity? It's going towards 0. So you are going to be asked to describe what happens as, like, for example, x approaches infinity. So we can say something along these lines, and this arrow indicates approaches. So y approaches 0 as x approaches infinity. Okay, those are things that you're going to be asked to describe here. What if I asked you, as x approaches 0 from the right? So here's what that means. Because I can approach they're both getting closer to 0. So this is going to have a stipulation which direction you're coming from. So what happens to the graph as x approaches 0 from the right? Y approaches what? No, y approaches infinity. Okay. So I know it's confusing because you're thinking about this is approaching 0, but what's actually happening to the graph as you move closer here? The graph is going up. Okay. So just be prepared to discuss and describe things like that. So we would say that y approaches infinity as x approaches 0 from the right. And I could ask you what it does from the left and so on. Okay. All right, what about this next section? Mallory, what did your graphs look like here? Okay, they were like, oh, that's a good way to describe it. In quadrant 1 and 2. Anything else that you noted? Okay, so closer to y-axis as we went from like -2 to -4. Okay. And again, let's discuss asymptotes. Where are they? What are we approaching but never reach? Logan, what are we approaching but never reach? The what? Okay, the x-axis and y-axis. Okay. All right, moving over to having fractional powers. Alyssa, what did these graphs look like? Okay, do it real quick. No, it didn't. You're just not getting a good.
Because that's all, I only put in one value.
Where are you seeing? Oh, you think those connect up there, maybe?
I think so, because I only put in x to the -2.
Okay. No, those are just going to keep going up.
Okay. Okay, thank you.
So what are these looking like?
They're all in the first quadrant.
Okay.
And they're kind of like arches going out to the right.
Okay, so we're looking at kind of arcs. What happens as we go from x to the 1/2 and then x to the 1/4? What's happening?
Is it like getting taller?
I don't know. You guys tell me. What happens as we move from x to the 1/2 to x to the 1/4 and so on? Hmm. Okay, so like this one would be to the 1/2, this one would be to the 1/4, and so on. Okay, good. I don't really have any other notes about this one. And then if we take those fractional powers and make them odd. Sydney, what did your graph look like here?
It looked kind of like the one before, only they were like closer together.
What do you mean?
I don't know. Like the lines were closer together. Yeah.
How would you describe what the graphs look like, though? Okay, what quadrants are like?
It's like 2 and 3. It's like a line.
I don't have mine in quadrants 2 and 3.
1 and 3.
Yeah, kind of like this, right?
That's
One-
not what mine looks like.
What?
That's not what mine looks like.
Make sure that you're putting those powers in parentheses, otherwise your calculator might not read it correctly. Okay.
How does it read it if it's not? What does it do?
It might read it correctly, but it might just read it as like x to the first times 3, like something like that.
Okay, I just didn't know what,
Yeah.
what it was.
This is it's a recliner. Can we call it?
A recliner. Okay, let's call it the recliner.
I like it.
So it is really helpful for you guys to kind of have a general idea of what these different functions look like in terms of their graphs. Will I like quiz you on it? Probably not, but it will just make your life a lot easier if you, again, have that general idea in your head. All right, the next thing that we are going to do, and I would like to get this example done before lunch, and then we'll just have a couple minutes after to finish up, is writing a power function given 2 points. So we've done this for lots of different types of functions throughout the year. So let's do it for a power function. I want to jog your memory that a power function is in the general form y equals k times x to the p. And honestly, what we're going to do, it feels a lot like how we set up finding an exponential function. So we're going to take each point, remember that each point is an x value and a y value, and we are going to plug those x and y values into this general formula. Okay, so for the first point, I will write 32 equals k, because I don't know that value, times 4 to the p. Just plugging in the values of x and y for that first point. I am going to do the same thing using the second point. So 1/2 equals k times 1/4 to the p. And then here's where it feels very, very much like what we did first semester writing exponential functions. We are going to take well, it doesn't really matter. We're going to take one of these equations and put it over the other. From here, we can simplify a little bit and solve. So first of all, I have k over k. I can cancel that out. I can take 32 divided by 1/2. Please don't tell me it's 16. What is it? 64. And then because both of these have a power or the same exponent, I can go ahead and divide those bases. So 4 divided by 1/4 is 16, and then to the p. Okay, how do we solve for an unknown exponent? Logs. You could take the common log or the natural log. I prefer natural log. So I'm going to take the natural log of both sides. I can then apply the power property and bring that exponent p down. This is a pretty basic log problem. Bring that exponent out to be a coefficient and then divide both sides by natural log of 16. And we get that our power in this function is 1.5. So we've done majority of the work, but we have the value of p. The other thing that we need to be able to write this function is the value of k. Once you know this value of p, you can take that and substitute it back into either one of these functions that you wrote at the beginning. I'm going to pick the first one because it doesn't have any fractions in it. So I'm going to say then 32 equals k times 4 to the 1.5. And then you can solve for k. So divide both sides by 4 to the 1.5. And just be careful when you put that in your calculator. Should be 4. Once you have your value of k and your value of p, then all you need to go back and do is actually write that function using those values.